Hey guys, my name is Laurent. I work for Happening, which is a sports betting and gaming organization in the UK. And this talk is also about Kubernetes, so bear with me. I know it's getting late in the afternoon. So I'm going to dive into it straight away. So the SRE team at Happening is handling the on-prem environment, which essentially is a Kubernetes cluster that's handling some data that we have to store in each country. And then that data has to be stored for 10 years approximately for regulatory purposes. So we have to deploy that in every country where we operate our services. So typically in Eastern Europe. And as I mentioned, it has to stay for a long time. And then we have essentially one cluster per edge on-prem env. And then we have to do like manual upgrades. There's a lot of maintenance that comes with that. So it's fairly intensive on the team. And then this is what an env at the edge looks like. So we have a virtual IP that's for the gateway. We have two essentially firewalls, gateways that we use for HA proxy and to expose our services. And then we have the control plane using kubeadm and a bunch of worker nodes for GB, Postgres, and some Kafka consumers. So this is pretty much that setup is times how many regions we have on-prem. Now, the vision. So this is what we thought as a way to essentially optimize the setup. So we decided to go with a centralized control plane on AWS. And then the data plane would remain at the edge. All the control plane nodes on AWS, worker nodes at the edge, and then we have a single way of deploying Kubernetes, which relies on EKS, which we already use on AWS in a few regions. And then this is broadly what we implemented. On EKS, which is the managed Kubernetes cluster on AWS, you can essentially define your remote node network and remote pod network. You can allocate a large CIDR for it. And VPC is like where we have the control plane and a bunch of other nodes if you want. And you need a private connectivity between your AWS region and then the on-prem side. And then on the on-prem side, you have your hybrid nodes, which it's called EKS Hybrid, the setup. And you have your gateway. So this is what I showed you in the previous slide. And then one of the requirements for that setup is that you need a sort of max round-trip latency of 200 milliseconds between AWS and on-prem. So in what we went with regards to the tunnel is we use WireGuard, it's very lightweight, very performant as a VPN protocol. It's quite recent. I think it's probably 10 years old. And then it's definitely a lot easier to set up if you look at IPsec and some of the AWS managed services like side-to-side VPN. So we are really happy with that. And it's got built-in encryption, which is obviously a requirement these days. And then the setup would look like we have a bunch of private subnets on AWS. We have some public subnets. And what we did is to enable essentially communication from the EKS control plane all the way to the on-prem ends is to have an auto-scaling group on AWS that essentially has at most one instance. And that means that when that instance goes down and then another one is being brought up, then that instance is going to look to get the ENI, so release it if it's already used, and allocate that ENI to the instance, dynamically update the routing tables for the private and public subnets so that the prefix lists for that particular region, everything is routed through the WireGuard interface. And then it goes through the tunnel, obviously. And then on the other side, you have also a WireGuard instance that essentially matches your AWS counterpart. So it's working great because we have literally had zero issue with it. And yeah, it's been proven. In terms of the CIDR planning, so this is I think the important part where I'm not going to go too much into the details, but we essentially allocated for the nodes /19 for essentially all on-prem regions. And then for the pod networks /17, which means that per market, so for each region, there's essentially up to 2,000 pods. And then the service side hasn't changed. So the important part here is that nothing should overlap. Otherwise, you're in for a world of pain. In terms of the CNI configuration, so we went with the recommended CNI approach that AWS has in place, which is a mixed mode CNI. The VPC CNI is the one essentially on the AWS side. That's the one that they maintain. And then Cilium for all of the edge regions. And then how did we manage to essentially have a centralized control plane that can serve all the regions is using that multiple IPAM feature in Cilium, which is, I think, is still in beta, but it's rock solid, it works fine. So we have a dedicated CIDR for each region so that control plane knows where to route traffic. And then we essentially define annotations in the namespace so that everything is propagated end to end. I'll show you in a sec. And this is what it looks like on the Cilium side. So we have a bunch of CRDs. There's loads of CRDs with Cilium. It can get quite complicated. But the first one is the node config from AWS. That's a managed CRD, which essentially we provision when we first create a node on-prem using Terraform. So pass this down as a config in the user inits, and we run like node ADM, and then essentially provisions a node with some labels. In this case, as an example, the region is Belgium, and then a taint as well, so that we don't want any workload that should not run in Belgium to run in Belgium, right? So we want to prevent that. The second part is whenever that node is being created on Kubernetes, then Cilium as an agent, the operator, is going to pick up that new node, and then it's going to match the label key, right? Like region is Belgium. Based on that, it's going to create a Cilium node, which matches the Kubernetes node, and then allocate it an IP from the IP pool Belgium, which is, again, another first CRD with the pod IP pool Belgium. And then that one has got a CIDR that is only for Belgium. And then the mask size, it means that it's going to slice /25 for every node in Belgium. And then the fourth thing that we've changed is the IPAM. We've injected an annotation for the IP pool of Belgium, which we're going to use later. This is the end result. We have one cluster for essentially all on-prem regions. Yep, so as you can imagine, whenever we need to go to markets and add some new on-prem regions at the edge, then we just need to essentially provision a new tunnel, which is a module. It's very simple, and then use the node ADM config in Terraform. So now we know how to route traffic for every on-prem node. The second thing that we had to deal with was how does the control plane reach the pods within a specific on-prem region? And then this is where BGP comes into play. So one of the features from Cilium is like dynamically handling routing using BGP. And this is how it looks like. So we have two nodes on-prem as an example, right? They all have an IP and a pod CIDR /24. And then these pods need to be reachable from AWS to on-prem, and obviously vice versa. The agent running on the node, the Cilium agent, is going to advertise the pod CIDR for the node through a BGP update, and it's going to send it to the gateway, which essentially, these are the firewalls that we have at the edge where we expose our services on-prem. That BGP update is going to update the route table. So at the gateway level, we have a tool called Bird. And then Bird, essentially, it acts as a relay for BGP, where it listens to the whole network for BGP updates. And then it's going to, whenever it receives a new announcement, it's going to update the routing table at the gateway level so that AWS, then it gets propagated to AWS, so that AWS, when it's trying to reach a specific pod that runs, for instance, in this node, it knows exactly how to do it all the way from AWS to on-prem because it's all done through BGP. And then again, what it looks like from the CDN perspective, we have a bunch of CRDs. This one is like anything that matches the label Belgium. We are going to expose the BGP routes to that instance. And that peer address is essentially firewall, the gateway one, where we run Bird as a relay. The second one is the peer config. That's where we define the families and what to essentially advertise. And then, the BGP multi-hop, which is quite useful whenever we have to do cross network to communication. And then the advertisement is what we want to advertise, which is you can advertise a service, you can advertise a pod IP pool, you can advertise many things. In our case, we want to advertise the pod IP pool because we want the pods to be reachable again from the control plane in case, for instance, there's some webhook that need to be injected, right? So great, now we have the nodes routing working, we have the pods routing working. How do we ensure that all of the workloads within, say, again, Belgium, since we use it as an example, how do we make sure that they stay in this market and they don't overspill to Germany or Serbia or any other country? And then this is where we use Kyverno, which is another open source tool. It's a mutation and validation controller. And it essentially ensures that the data stays in the market and there's no cross-market shielding by acting as a mutation controller whenever a new pod is being launched into a namespace. Example here, we have a cluster policy that's been deployed, on a cluster. And then whenever any pod is launched in the namespace, let's say Belgium again, we, using the CEL, that's the Common Expressing Language, we essentially query the AP1 V1 namespaces from the pod that's being launched. Then essentially that's the namespace Belgium. And then we get the GMES path for that particular namespace. And using the label, the annotation, IPAM Cilium IP pool. That's the one I showed you before that we injected in every namespace for on-prem. And then using that, it's gonna return the market, which is Belgium. Then we are going to mutate the pod and inject the node affinity and then the toleration. So with all of this in place, then the pod will be scheduled into Belgium. And then this is something that can't be changed. So it's a safeguard essentially for any of the workloads in any market. And again, it's been working great so far. I'm going to mention this particular policy. It's a lot of CRDs. This one came out last month from Kubernetes 1.34. And it's essentially a mutating admission policy that could be a good replacement for Kyverno out of the box. It basically does the same job. It just matches conditions, and then it can mutate the pods and any other resource. Okay, we've got all of the three requirements now. Let's quickly talk about the DNS resolution. Another requirement is that we wanted DNS obviously to work the same way it used to work on-prem with that new setup. And we didn't want the AWS side, which is where we run our critical services, to be affected by any change in DNS. So what we did is we installed something called node-local DNS, which is essentially a daemon set that you run on your on-prem nodes. That's why we run it anyway, but you can run it anywhere. And then it's actually caching the DNS requests at the node level so that you don't have to hit core DNS every time or whatever DNS you're using. But the out-of-the-box one is core DNS. So you've got the pod that's essentially requesting, any DNS resolving for something that runs potentially on-prem. It's going to first go to node local DNS, and then if there's a hit, it goes back to the pod. If there's no hit, then it goes to core DNS. And as a failover, if it's not working, then we can bypass node local DNS and go straight to core DNS. So we haven't made any changes to core DNS because we didn't want the latency to be affected essentially for the critical services by potentially having some pods running on-prem. And we also wanted to be able to resolve some of the non-Kubernetes records that were in the on-prem region, A side note, again, Cilium being Cilium, it's very powerful because you can use load balancing through eBPFs. But here it was essentially bypassing the request from the pods and then routing directly to core DNS. So we had to install a local redirect policy, which forces for any of these ports, local resolving first and then core DNS. So this was very useful to know. And then the results. So in terms of the management overhead, down 60%, at least, I think, because we don't have to run Ansible for the on-prem nodes and then the control plane as well. We only have a single Terraform module that's very easy to use. We can just bump the Kubernetes version whenever we do an EKS upgrade, and then it just works out of the box. Upgrade time, that includes obviously the prep and looking at the potential issues. Also went down massively. I said 2 hours. It's give or take based on the Kubernetes version. Some are they've got more changes, some have less. Amount of control planes obviously went down massively. Now we use a single control plane for everything. And then the latency actually went up, obviously, because now we don't have we don't have the control plane on-prem. We have control plane on AWS, which does add some latency, but for us, this is not an issue at all. We are fine with that. And then I'm quoting 30 milliseconds. That's from Germany, where we have the AWS region, the main one, to Malta or Greece, for instance. These are the further away ones. But if it's in Croatia or some other countries, technically it's more around 15 millisecond round trip. In terms of the key benefits, I think I've mentioned them before, but yeah, we essentially now use EKS for everything, which is great because it's a lot easier to maintain across the company. And yeah, any operation is a lot quicker. Lesson learned, which I think is very important. The slider planning, we probably spent a lot of time on that, making sure that we have the right allocations, enough space for potential expansion in each region. BGP is something that we did spend a lot of time on. Understanding how BGP works is very useful. And in terms of the connectivity, the VPN, making sure that if it goes down, what happens? For instance, if your link between on-prem and AWS goes down, does your cluster still behave as normally? Does it fail? The MTU is something that was probably the part that was the most difficult to get, because on AWS, you've got some AWS instances that have Jumbo frames enabled, which obviously doesn't work well with the edge side. So we had to lower the MTU and have it the same pretty much end to end. And then finally, do what works best for you. I think that makes sense. If you are running some critical services at the edge or on bare metal or on VMware, wherever, might make sense to keep the control plane, because if it goes down, and it could be an issue of a few days. For us, it's a perfect use case because we can tolerate an outage for this on-prem at the edge regions, because it's only for regulatory purposes. So we can have some sort of downtime over a few hours based on the market. Since we use Kafka anyway to replicate data between AWS and on-prem, so it's going to resume at some point. It's just that there might be a lag, but that's okay. So yeah, again, do what works best for you. And that's it, really. Does anyone have any questions? Oh, sorry.
So you said you needed to be careful to schedule the workloads on a specific market. Do you also need to be careful about cross-market network communications, so that, for example, workload that is scheduled in Belgium, it doesn't reach out to a workload in another region? How do you think about this?
Yeah, it's a very good point. So because of the way the networking has been set up, there's no way that it works, because the on-prem, Belgium, for instance, doesn't know how to route to Croatia. It just knows that the AWS side, this is how it should go to AWS, but there's no way from AWS to route back to Croatia. This is just not happening. As an additional measure, though, we did consider using network policies, which is another Cilium feature, but many CNIs have it, to disable that, to make sure that there is really not like an air gap setup, but there is no cross-market communication. But the way that it's set up at the moment, we just don't need to because it's very much impossible.
Okay, you filtered the BGP routes on the side so it doesn't propagate to another edge region.
It's just like not even talking about BGP. If you try to reach from Belgium from a pod that lives in Croatia or somewhere else, there is no route for it in Belgium. The only routes that are available, they are the routes on the AWS side. So there is no way that it essentially goes through AWS and back to another market. Yeah, that's it. Yeah, very good question.
Okay, thank you.
All good? Oh, sorry.
Yeah. How do you manage the update? Because with one cluster, one control plane, if something goes wrong, like you didn't see it coming, you will be impacting like the entire markets across your different clients, right?
Yeah, that's a good question. So we have AWS. Most of the services are in Frankfurt in Germany. We also have some services in Dublin and in Sao Paulo. And we tend to use these clusters as not a test bed, but because we have less resources on them, we tend to use them for when we upgrade on stage and pod. We do typically do the upgrades on these ones first, and then on the UC one. Yeah, and that's enough. I think. Obviously, we do quite a thorough. We have a checklist of everything to validate before an upgrade. But we haven't really come across any issues. Like we obviously check the AMIs and all that to make sure that EKS Hybrid setup, but it's fine for us. Yeah.
Okay. And another question,
Yeah.
Since it's quite a complicated system, do you manage to have a staging or pre-prod environment that's close to what you are doing in production?
Yeah, we have the same. So we have a one-to-one mapping between stage and pod. So it's all, yeah, whenever we do make changes, we tend to do them on stage, especially I'd say the tricky part is the Cilium upgrade. Because Cilium, whenever they upgrade the Cilium tool, right? Whenever there's a new release, there's a lot of changes with it, and then it can get quite complicated. So we do tend to have some tests in place. And then the thing that we are doing at the moment that we're working on is how do we validate that whenever we do a Cilium upgrade, for instance, or like an EKS upgrade, everything works on the network inside. So we are setting a black box exporter and a bunch of other things to ensure that a pod on-prem can reach AWS, that the control plane can reach a specific pod, that some of the features on AWS credential injection, which is using like service accounts when some services on-prem can access some buckets on AWS. All of this stuff works essentially, right? I think that's the thing that we want to test. So we are doing more like end-to-end testing to validate that a setup works fine, because obviously it's quite difficult to test every single feature. Yeah. That's what we're looking.